Hello everyone. This chapter I'll talk about technical principles of Spark. After this course, we'll be able to understand application scenarios and master highlights of Spark, master the computing capability and technical framework of Spark. Also, we can master the integration of Spark components in Fusion Insight HD. So first, what is Spark? Spark is a distributed computing engine based on memory. It stores the intermediate processing data in memory. This is the feature that different from traditional computing engine like MapReduce. Then what does Spark provide? Spark provides a one-stop data analysis capability and supports flow-based processing in small batches, offline batch processing, SQL query and data mining, graph computing, and machine learning. Users can seamlessly use these functions in an application. In practical use, for example, batch processing can be used for data ETL, which is to extract, transform, and load data. Machine learning can be used for shopping websites to judge whether customer reviews are good or bad. And SQL query can be used for query data in Hive. And stream processing is applicable for real-time services such as clickstream analysis, recommendation system, and public opinion analysis. Take a look at some key features of Spark. First, light. Spark uses Scala language, which is much more simple and vivid. Besides, it uses infrastructure of Hadoop and Mesos, which is also an open-source framework to manage computer clusters. So Spark has only 30,000 lines of core code. Second, fast. Spark has sub-second level latency for a small dataset. Specifically, Spark has higher speed compared with MapReduce or Hive for large dataset applications such as iterative machine learning, ad hoc query, and graph computing. Besides, Spark is featured with in-memory computing, data locality and transmission optimization, and scheduling optimization. Third, flexible. Spark provides flexibility at different levels. For example, Spark supports new data operators, new data sources, and new language bindings. And Spark supports a variety of functions, such as in-memory computing, multi-iteration batch processing, ad hoc query, streaming, and graph computing. The last one is smart. It uses existing big data components. To be more specific, Spark seamlessly integrates with Hadoop, and graph computing uses Prego, Power Graph APIs, as well as Power Graph point of division. Prego and Power Graph both are distributed graph parallel computing framework. Based on this figure, we can see that Spark is capable of interacting with multiple applications, environments, or different data sources, such as Hive, Apache Hadoop, and MySQL HBase. We've learned MapReduce before. It's also a computing model framework, and it's used for parallel computing of a massive dataset. And in MapReduce, intermediate data generated by map tasks will be written to local disks as MOF, which is mapout files, waiting to be obtained by reduce tasks. But the intermediate data of Spark is stored in memory. So Spark improves the computing efficiency and reduces the delay of iterative operations and batch processing. Besides, Spark is suitable for iterative computation. If repeated operations increase, more data needs to be read, and Spark computing brings greater benefits because intermediate data of Spark is stored in memory. So the performance of Spark is over 100 times higher than that of MapReduce in specific scenarios with multiple iterations. For scenarios with fewer iterations, Spark does not have many advantages over MapReduce. Spark also provides more flexible programming model and higher development efficiency because Spark provides more dataset operation types. And Spark has higher fault tolerance capability because of lineage mechanism. I'll explain this mechanism later. Take a look at this figure to show the difference more intuitively. In MapReduce, we read data from HDFS. After first iterative computing, we'll save the intermediate result on the disk. Then, make second processing. Results of every iterative computing need to be written in disk. But in Spark, intermediate results do not need to be written in disk. It's stored in distributed memory, which improves the computation performance. And this table shows that the performance of Spark is much better than that of MapReduce. The resources, including the number of nodes and cores needed for computing in MapReduce, is almost 10 times of that in Spark. But Spark provides the performance by more than 3 times. Next, let's talk about Spark principles and architecture. The first one is Spark Core. This is the system architecture of Spark. The green part is the new function of Spark version 2. At the bottom is the standalone scheduler, which is a resource management framework that comes with Spark. It also supports the resource management systems of Yarn and Mesos. But Fusion Insight integrates the Spark on Yarn mode by default and does not support other modes currently. In the middle is Spark Core. It's a distributed computing framework similar to MapReduce. The intermediate computation result is directly stored in memory, which improves the computation performance. On top are some functional modules. Spark SQL is a Spark component mainly for processing structured data and conducting SQL-like queries on data. By using the Spark SQL, ETL operations can be executed based on different data formats, such as JSON, Parquet, and ORC, and data sources, like HDFS and database, to complete specific query operations. Structured streaming is an engine built on Spark SQL to process streaming data. It's programmed by using Scalar and it's fault tolerant. Spark Streaming is a streaming engine for micro-batch processing. Stream data is sliced and then processed in the computation engine of Spark Core. Compared with Storm, it provides weaker real-time performance, but better throughput. And MLlib is Spark's machine learning library. Its goal is to make practical machine learning scalable and easy. GraphX is a new component in Spark for graphs and graph parallel computing. GraphX includes a growing collection of graph algorithms and builders to simplify graph analytics tasks. Spark R is an R package that provides a lightweight front end to use Apache Spark from R. In Spark version 2, Spark R provides a distributed DataFrame implementation that supports operations like selection, filtering, aggregation, and so on large datasets. Spark R also supports distributed machine learning using MLlib. Spark revolves around the concept of RDD, which is Resilient Distributed Dataset. RDD is a fundamental data structure of Spark. It's a read-only partitioned collection of records. RDDs are stored in memory by default and will overflow to disks in case of insufficient memory. Each RDD is divided into logical partitions, which may be computed on different nodes of the cluster. This feature improves performance by data locality. There are two ways to create RDDs. An RDD can be created from a Hadoop file system such as HDFS, or a storage system that Hadoop is compatible with. Alternatively, an RDD can be converted from a parent RDD. Besides, RDD supports a lineage mechanism, which indicates the dependency chain. An RDD remembers how it evolved from another RDD using a lineage. So in this case, data can be recovered quickly when data loss occurs. There are two types of dependency of RDD, narrow dependencies and wide dependencies. Narrow dependency indicates that each partition of the parent RDD is used at most by one partition of the child RDD, while wide dependencies indicates that each partition of the parent RDD may be used by multiple child RDD partitions, which is the basis of stage division. There are some advantages of narrow dependency. First, narrow dependency supports execution of multiple commands in pipeline mode on the same cluster node. For example, after the map operation is performed, the future operation can be performed immediately. Second, failure recovery of narrow dependency is more effective because only the lost parent partition needs to be recomputed, and the recomputation can be performed concurrently on different nodes. It's very difficult to divide stages in a submitted job due to complex RDD dependencies. In this case, Spark uses narrow dependencies and wide dependencies that are mentioned before. Spark Scheduler reversely traverses the whole dependency chain from the end of the DAG. When a wide dependency is encountered, the dependency chain is broken. When a narrow dependency is encountered, the RDD partition is added to the current stage. The number of tasks in a stage is determined by the number of RDD partitions at the end of stage. RDD conversion is a partition-based coarse-grained computing, and the result of a stage execution is the RDD of these partitions. RDDs support two types of operations, transformation and action. For example, map is a transformation that passes each dataset element through a function and returns a new RDD representing the results. On the other hand, reduce is an action that aggregates all the elements of the RDD using some function and returns the final result to the driver program. All transformations in Spark are lazy, in that they do not compute their results right away. Instead, they just remember the transformations applied to some datasets or files. The transformations are only computed when an action requires the result to be returned to the driver program. This design enables Spark to run more efficiently. For example, we can realize that a dataset created through map task will be used in a reduce task and return only the result of the reduce task to the driver, rather than the larger mapped dataset. Then let me introduce some major roles of Spark. Driver is responsible for the application business logic and operation planning. Application master is used to manage application resources and applies for resources based on applications. Client is to submit applications. Resource manager is responsible for scheduling and allocation of resources in the whole cluster, and node manager is responsible for resource management of each node. Executor is the one that really do the tasks. An application will be split for multiple executors to compute. The Spark computing and scheduling can be implemented using Young mode. Spark enjoys the computing resources provided by Young clusters and runs tasks in a distributed way. Spark on Young involves two modes, Young client and Young cluster. In Young client mode, the driver is deployed and runs on the client. During the operation process, the client first sends the Spark application request to Resource Manager, and the client packages all the information required to start Application Master and sends the information to Resource Manager. Then, Resource Manager returns the results. The results include information such as application ID and the upper limit as well as lower limit of available resources. After receiving the request, Resource Manager finds a proper node for Application Master and starts it on its node. Application Master is a role in Young, and the process name in Spark is Executor Launcher. Based on the resource requirements of each task, Application Master can apply for a series of containers to run tasks from Resource Manager. After receiving the newly allocated container list from Resource Manager, Application Master sends information to the related node manager to start the container. Resource Manager allocates a container to Application Master. Then, Application Master communicates with the related node manager and starts Executor on the obtained container. After Executor is started, it registers in driver and applies for tasks. Then, driver allocates tasks to Executor. Executors do the tasks and report the operating status to driver. And the Spark on Young cluster implementation process is as follows. Client first generates the application information and then sends the information to Resource Manager. The Resource Manager allocates a container to Spark application and then starts driver on the container node. After that, Application Master applies for resources from Resource Manager to run Executor. The Resource Manager allocates a container to Application Master. Application Master communicates with the related node manager and starts Executor on the obtained container. After Executor is started, it registers in driver and applies for tasks. Then, driver allocates tasks to executors, and executors do the jobs and report the status to driver. So what's the difference between Young Client mode and Young Cluster mode? The first one is Application Master. In Young Cluster mode, drivers runs in Application Master, which is responsible for applying resources from Young and monitoring the running status of a job. When a user submits a job, client can be closed and the job continues running on Young. However, the Young Cluster mode is not suitable for running interactive jobs. In Young Client mode, Application Master applies only Executor from Young. Client communicates with the obtained container to schedule tasks. Therefore, client cannot be closed. And Young Cluster is suitable for production because the outputs of applications can be quickly generated, while Young Client is suitable for testing. Besides, if the task submission node in Young Client mode is down, then the entire task will fail. But this kind of situation in Young Cluster mode will not affect the entire task. Let's take a look at a typical case word count based on Spark. At first, use command text file to obtain data from HDFS and process in the form of RDD. Then, Invoke flag map to split text into words, and then do map operation to denote the frequency of appearance of each word as one, and then invoke reduce by key to merge the counts of each word, and finally invoke save as text file to import processed data into HDFS. Here, until the save as text file command is executed, the whole Spark computing processing is starting. All the four previous operators are the transformation operators, and only the save as text file is the action operator. The next part is about Spark SQL and Dataset. Spark SQL is a module for processing structured data. In Spark application, SQL statements or DataFrame APIs can be seamlessly used for querying structured data. Simply speaking, Spark SQL is just a module that can parse SQL language to RDDs and then use Spark Core to execute. This graph here is to show you the process of parsing SQL language to RDDs. Here, DataFrame is a distributed collection in which data is organized into named columns. Spark SQL and DataFrame also provide a universal method for accessing multiple data sources such as Hive, CSV, ORC, and JSON. These data sources also allow data interaction. Spark SQL reuses the Hive front-end processing logic and metadata processing module. With the Spark SQL, you can directly query existing Hive data. In addition, Spark SQL also provides API, CLI, and JDBC interfaces, allowing diverse inputs to the client. A dataset is a strongly typed collection of domain-specific objects that can be transformed in parallel using functional or relational operations. Datasets are similar to RDD, but does not use Java serialization or Creo encoders to serialize objects for processing or transmission over the network. Encoders and standard serialization are responsible for serializing an object into bytes. Encoders dynamically generate code and use a format that allows Spark to perform many operations, such as filter, sort, and hash without deserialization bytes into objects. Each dataset also has an untyped view called a DataFrame, which is a dataset of row. DataFrame is a structured distributed dataset composed of several columns, which is similar to a table in the relational database or the DataFrame in R or Python. DataFrame is a basic concept in Spark SQL and can be created by using multiple methods, such as structured dataset, Hive table, external database, or RDD. DataFrame has data structure information, which is schema. RDD, datasets, and DataFrame are compared. For RDDs, both cluster communication and I/O operations require serialization and deserialization of data and data structures. Datasets and DataFrame have exactly the same functions, but the different types of the data in each row. For DataFrame, data in each row is of the row type. Fields and types of these fields in each row are unknown. You can only use getAs or pattern matching in the common to obtain a specific field. In a dataset, the type of each row is not fixed. After defining the case class, you can obtain the information in each row. Information in columns of DataFrame is clear, but that in rows are unclear. Compare Spark SQL with Hive. Spark SQL uses Spark Core as its execution engine, while Hive uses MapReduce. and the execution speed of Spark SQL is 10 to 100 times faster than Hive. Spark SQL syntax and Hive syntax are basically the same except for bucket operations. Besides, Spark SQL depends on the metadata of Hive, and it's compatible with most syntax and functions of Hive. It can also use user-defined functions in Hive. Then, let's take a look at Spark structured streaming. While structured streaming is an engine built on Spark SQL to process streaming data, it's programmed by using Scalar and its fault tolerance capability. Streaming computing processes are compiled similar to the application of static RDD data. If streaming data is incrementally and continuously produced, Spark SQL will continue to process the data and synchronize the result to the result set. Similar to the data block processing model, the streaming data processing model applies query operations on a static database table to streaming computing, and Spark uses standard SQL statements for query to obtain data from the incremental and unbounded table. Consider the input data string as the input table. Every data item that is arriving on the string is like a new row being appended to the input table. Each query operation will generate a result table. At each trigger interval, updated data will be synchronized to the result table. Whenever the result table is updated, the updated result will be written into an external storage system. And there are three types of storage modes of structured streaming at the output phase: complete mode, append mode, and update mode. For complete mode, a connector of an external system writes the updated result set into the external storage system. For append mode, if an interval is triggered, only added data in the result table will be written into an external system. This mode is applicable only to a result set that has already existed and will not be updated. For update mode, if an interval is triggered, only updated data in the result table will be written into an external system, which is the difference between the append mode and update mode. To illustrate the use of this model, let's understand the model in context of the word count example here. The first line's data frame is the input table, and the final word count's data frame is the result table. Note that the query on streaming line's data frame to generate word counts is exactly the same as it would be a static data frame. However, when this query is started, Spark will continuously check for new data from the socket connection. If there is new data, Spark will run an incremental query that combines the previous running counts with the new data to compute updated counts, as shown here. Note that structured streaming does not materialize the entire table. It reads the latest available data from the streaming data source, process it incrementally to update the result, and then discards the source data. It only keeps around the minimal intermediate state data as required to update the result, such as the intermediate counts in this example. The last one is Spark streaming. Spark streaming is a real-time computing framework built on the Spark, which expands the capability for processing massive streaming data. Data can be ingested from many sources like Kafka, HDFS, and can be processed using complex algorithms expressed with high-level functions like map, reduce, join, and window. Finally, processed data can be pushed out to file systems and databases. The basic principles of Spark streaming is to segment the input data by second or millisecond, and periodically submits the data after segmentation, which decomposes streaming programming into a series of short batch jobs. While simply speaking, it works as follows. Spark streaming receives live input data streams and divides the data into batches, and then are processed by the Spark engine to generate the final string of results in batches. One more thing to notice is that Spark streaming provides a high-level abstraction called discretized string or dstring, which represents a continuous string of data. These streams can be created either from input data streams from sources such as Kafka, Flume, or by applying high-level operations on other dstreams. Internally, a dstring is represented as a sequence of RDDs. Spark streaming performs computing based on RDDs, so any partition encountering errors can be regenerated based on the parent RDD using the RDD lineage mechanism. If the parent RDD is lost, look up for its parent RDD until the original data in the disk is found. At last, let's take a look at the Spark integration in Fusion Insight HD. Fusion Insight Manager provides a virtual web UI for Spark, allowing users to obtain information about the service status, roles, and open configuration items, perform management operations such as starting and stopping Spark, downloading the Spark client, and synchronize configurations, and also can view the running instance health status and service overview. In the Fusion Insight cluster, Spark interacts with the following components. For example, Spark reads or writes data in HDFS, Yarn schedules and manages resources to support the running of Spark tasks. Spark SQL shares metadata and data files with Hive, and HA of JDBC server depends on the coordination of Zookeeper. JDBC server provides the JDBC interface for directly sending external JDBC requests to compute and parse structured data. The first four are mandatory. Besides, Spark can receive data streams sent by Kafka, and it can perform operations on edge-based tables. These two are optional. So this chapter mainly talks about Spark, including its background, application scenarios and characteristics, basic concepts, technical architecture, task running process, Spark on Yarn, and application scheduling. Also, I've introduced the integration of Spark in Fusion Insight HD. Okay, that's all for Spark. Thank you.